what you see here is an alcohol, right? So you gotta search your mind that what is any reaction that makes an alcohol? Then we will talk about several things, right? Hydration reactions, oxymercuration reactions, hydroboration reactions. Then those are the ones that you're adding water to double bonds. So this is probably what you need to make that. I mean, I'm trying to figure things out backwards. So something called retrospective analysis. So if you have that, you can do this. The question is, yeah, that's one thing. What reagent would you need to do? That depends on, is this a Markov-Nico product or anti-Markov-Nico product, right? So again, to sort it out, Markov-Nico products have a nucleophile on more substituted double bond, more substituted side. This is the more substituted side compared to that. That's the where it OH is sitting. So that's Markov-Nico products. So what reaction you need? You need oxymercuration, demercuration. Mercury acetate, insoluble hydride. Then you do this, not the hydroboration, right? Then how are you gonna make that from this? Making double bonds from the alkyl halide is something that we already talked about in the previous chapters. I hope you remember that is the E2 elimination reactions. So that's why you cannot simply cut away test material, test 2 material, because we build on it. So put it together. First thing is you make a double bonds, that's E2 elimination reactions. You can choose a p-butoxide, that's fine, you know. And then oxymercuration, demercuration, you know, that you can make these things happen. Yeah.
That's it. That's it. Photo concentration.
Yeah, it'll be slow down.
And then what I was wondering is, can't you do SN1 with just water?
Then you're going to mess it even completely. So these ones are something we already talked about, but the things I just want to show is a pair. So you see the differences. If you have to make this from that, always sitting on the more substituted side. If you have to make that from this, always sitting on the less substituted side, you can clearly see that the position differences requires different reagents, right? This was a Markov-Nico product, more substituted carbon getting a nucleophile. This is an anti-Markov-Nico product, OH sitting on the less substituted side, right? That's something that you really have to know. And then, once you know that, then you need to remember that if you want to add the water to the Markov-Nico fashion, that will be the oxymercuration, demercuration. If you want to do this, that will be the hydroboration. So you can sort of like a map things easier once you do the initial analysis. Showing you the mechanism, mercury acetate makes a bridge ion, just like this. Waters makes an attack on the more substituted carbon, because of more substituted carbon, we have a more complicated characters built on. The water makes an attack with the opposite side. Mercury goes the other way, and then mercury replaced by the insoluble hydride. Then you get these things prepared. I mean, didn't really show the stereochemistry, but this was done needed anyway. Hydroboration, on the other hand, you get H and BH2 added on the same side, right? It's a conserving mechanism. Bigger BH2 oriented itself on the less substituted side. Smaller hydrogen on the more substituted side. That's why we get the anti-Markov-Nico orientation. BH2 replaced by the OH. That's on the second part, oxidation. And then you got OH sitting on here, hydrogen sitting on there. So that's the difference between those two. So something that you really have to be aware of. I'll give you 5 minutes. All right, anyway, those are simple. After seeing that, this is a question I asked you. We did this question last class, so you know these things. But I'm telling you, not right now. Not right now, you probably know. I mean, maybe we forgot, but anyway. Later on, you have to find out a reaction to make these things. And then, I know, you research in your mind that do I know any reaction that took the OH? Then, because we emphasize so much of the hydroboration, oxymercuration, demercuration, some of you may think that, oh yeah, this can be made by that. Then let me show you. This is what we did. But if you try to do oxymercuration, demercuration, does it work? I mean, you can prepare double bond from that, that's fine. But if you have a double bonds, if you do the oxymercuration, demercuration, can you get that? It puts this, but not that. But sometimes your minds are so focused, and I gotta put on OH. And then the reaction that I know putting the OH is oxymercuration, demercuration, or the sodium hydroboration. So you may answering like that. If you do hydroboration, then would you make this from that? Still no, because they put OH with the hydrogen, not the chlorine. So you really have to pay attention to what else comes together. They may looking similar, but these things are made this way. It's a chlorohydrin. You get the chlorination done first, then opening up with the water. That's a chlorohydrin reaction. So having chlorine there makes it different question. If you try to handle by the additional water, you're gonna make this, not that. You're gonna the chlorine missing. And then you may think that, okay, I'll do this. I'll add chlorine there later. But believe me, chlorine adding on this carbon later is difficult. It's not something I can think of easy way either. So sometimes not rescuable. So you really have to get the right way. If the chlorine and then OH, they are adding it together, they have to be trans. If I put the chlorine and OH on the same side, that's even different question. So every reaction, you gotta understand what it does, and then you put the whole thing, not just OH part. I know why people do that, because they don't understand, they're trying to find out something out of that situation. They thought that, okay, OH there, gotta be the adding water. They answer this way. Unfortunately, this makes this, not that. So we have to just cross it away, wrong answer. And then they're gonna come back and say, oh, it's OH there, I should have credit. No, it's a different mechanism, it's a different thing. So similarity doesn't really work here. If you go on later, instead of just one letter differences in the chemical structures, that change the whole thing. You're gonna see that. If people argue about, I just miss a one letter. H has becomes a CL, what makes differences? If you think that way, this is not the class for you, believe me. Subtlety is a one way you really have to look for. Everything must be right. There's nothing with similarity within chemistry. It's going to be tricky for you. So anyway, I get many of the people answering this way, and then that's wrong answer. I just want to use this example to show you that it's got to be right in every way, not just half right. That's things we talked about: the fluorohydrogen information, the halohydrogen information. The halogen comes with the OH. It got to be trans, and then again, this thing doesn't matter about the OH. Has to go to the lower substituted side in order to this becomes a chlorohydrogen reactions. If somehow you get the chlorine here, hydrogen there, but the hydroxyl goes to the less substituted side, chlorine the more substituted side, that's not even the right product for the chlorohydrogen reactions. So that is even different things.